In this video, we're going to look at 3 different problems that involve F equals ma, and they're going to be slightly more complicated than in the previous video. So pause the video now and try question 1. The first part asks us to find the tension in the cable. So let's label the tension. Now, importantly, we've been asked to assume that they are stationary. So because they're stationary, and actually, well, not because they're stationary, because it's one single wire, one single string, the tension must be the same everywhere. If the tension was not the same, then there'll be some net force on the string and it would cause it to accelerate. So the tension, importantly, is the same. So what is the tension equal to? Well, it must be equal to the weight in order to balance it. So we've got tension equals 1.5 G plus 8G. So let's put that in our calculator. So that is 9.5 times 9.8, which is 93 newtons. Now you might say, oh, hang on a second, aren't there 2 tensions? Aren't there two pointing up? Shouldn't we divide this by 2? Well, the answer is no, because what you've got here is, one thing that the string is resting on, and we've got this 8 kilogram pulling down here. We've also got this 1.5 kilograms pulling down in the direction. So we've almost got one piece of string that we're stretching from both ends. So the tension is actually going to be the sum of both of them. In part II, the masses are released, finds the acceleration. So instinctively, we know that it's going to accelerate down this way because this one's heavier, and it will accelerate up in this direction here. And the acceleration must be, so what we need to use is, of course, F net is mass times acceleration, and we need to apply it separately for each mass. So let's do it for the 8 kilogram mass first. We've got the weight minus the tension is the mass times the acceleration. And for the 1.5 kilogram one, we've got the tension minus the weight equals the mass times by the acceleration. Now, you might say, hang on a second, shouldn't this acceleration be negative? Well, it's not in this case. And the reason is that in both of these cases, I've worked out my resultant force to ensure a positive acceleration. So I'm saying this is accelerating downwards. So 8G minus the tension means I've got downwards acceleration. And in this equation, I've said the tension minus the weight is mass times acceleration. So I've said my acceleration is up, and that's what's positive. So again, maybe that doesn't actually explain it. But what I could also say is if I always treat up as positive, for example, then I could have said 1.5 G minus tension is minus the acceleration. And here you can see that this is the same equation, but I've taken the direction as opposite. So there's nothing wrong with doing it this way as long as you're clear, but I think this way is just a little bit simpler. So let's use this way. We now need to solve these simultaneous equations. Now you could, of course, substitute in the tension and work it out, but often we're not encouraged to find the tension, and so the quickest way is just to solve these simultaneous equations, which we can do really easily by adding them together, because then the t's cancel. So if we add them together, we get 8G minus t plus t, which obviously cancels out to 0, and then minus 1.5G equals 8A plus 1.5A. So then we've got 8G is 9.5A, which means the acceleration is 8 times by 9.8 divided by 9.5, which is 0.09 meters per second squared. Pause the video now and try question 2. So as usual, we should sketch out a quick diagram. So we have a sloping surface that is at 33 degrees to the horizontal, and we have a shoe, maybe it's on an icy roof, of mass 0.8 G, and it slides down this way with some velocity or some acceleration. So it says calculate the acceleration. So again, we can use SUVAT for this. So its initial velocity is 0. Its final velocity we don't know, but we don't actually need to work out. Its acceleration we are trying to work out. The time we're given is 3.1 seconds, and the so the displacement is 3.1 seconds. So acceleration is, well, probably we would start with S is ut plus half at squared. Now u is 0, so this just becomes 0. So acceleration is therefore 2s over t squared. So 2 times 2.6 over 3.1 squared, which means our acceleration is 0.54 meters per second squared. What is the frictional force? So what's actually going on in this situation? We've got this force acting down the slope, and that is the component of the weight. And then we have now got some friction acting backwards. So in order to work out the frictional force, we could, if we knew what the coefficient of friction was, work it out that way, but we can use Newton's second law. So the net force is mass times acceleration. So what force is down the slope is this component here, which is going to be mg sine theta. So this is theta, which is this angle here, minus the friction equals the mass 0.8 times acceleration 0.54. So we can work out our friction by rearranging this equation, and that's going to be equal to 3.8 newtons. Okay, question 3. Pause the video now and try this question. So here we have a ball bearing being dropped into oil, and it is moving down at its terminal velocity because it's reached that very, very quickly, as we've been told. So what is its terminal velocity? Well, we can work that out using SUVAT. So we've got our distance of 0.350, our time of 6.2 seconds, u is 0, and acceleration is going to be we don't know what its acceleration is going to. Well, we do know what's acceleration. It's moving at a constant velocity because it's at its terminal velocity, so its acceleration is 0. So all we really need to do is velocity is displacement over time, which is 0.350 over 6.2. Which is 0.06 meters per second. What is the drag force on it? So we need to use the resultant force as mass times acceleration, where we've got the resultant forces, its mass times its gravity weight minus the friction that is on it, which is its drag, equals its mass times acceleration. So drag is mg minus ma, which is 0.1 9.8 minus its acceleration, which is 0. I've just complicated things for no reason here, really. There is no acceleration, so the drag is literally equal to its weight, which is 0.1 times by 9.8, which is 0.098 newtons. So if there was an acceleration, we would use this full form, but we could say this is 0 because it's moving at its terminal velocity.